let's talk about the chain rule. So recall that the chain rule is a rule for differentiating the composition of two or more functions. And so it's a shortcut for determining the derivative of a combination of functions, in particular the combination of composition. Okay? And so I've put a couple of examples here to show you the rule for the chain rule. That is, if we have h of x, if it's defined as a composition of two functions where it's f composed with g, that is, f's input is replaced by g's output. Okay? Remember that the input of the function is just the stuff that we're plugging into the function. Okay, that's the variable. The variable of f is g, and the variable of g is x. And so if I want to take the derivative of h with respect to x, which is the variable of the g function, I have to go through f, g, and then finally go through x. Okay? So because I have a chain of functions here, f to g to x, I have to have a chain of derivatives when I'm finding the derivative of this composition of functions. Okay? Remember that the derivative tells you the rate of change of the function with respect to an input. And so if I want to know the rate of change of the function h with respect to g's input, I have to find the rate of change of f, the outside part of this function, with respect to g. G is f's input. Okay, so I have to go from f to f's input, which is g, and I have to multiply that by the way that g changes with respect to its input, which is x. Okay? So that means that the derivative of h with respect to x is the derivative of f with respect to g. Okay? That's f with respect to its input, multiplied by the derivative of g with respect to its input, x. Okay? So it's df dg, dg dx. And recall that you can think of each one of these little pieces here, this Leibniz notation, as really a ratio, or that is a fraction of an object. Okay, so it's df dg over dx gg. And if I cancel out the dg's, you can see you get back to dh dx. Okay. Similarly, if I have a function of a composition of three functions, okay, we have a chain of three derivatives, and it keeps going. So you can certainly embed many different functions. There's nothing stopping you at one. And I just wanted to show you that you can define k of x as a function of a, which is a function of b, which is a function of c, which is a function of x. Okay, and it all gets very complicated after a while, but there's nothing stopping you from going to more functions. Okay, and in this case, I know k is a function of a, which is a function of b, which is a function of c, which is a function of x. And all that happens is, if I want to know how k changes with respect to the innermost input, x, then I have to go through from a to b, then from b to c, and then finally from c to x. Okay, so I have to go from a to b to c to x. All right? And so this is the chain rule. This tells you how the outside function is changing with respect to the innermost input. And it turns out that this kind of function, the composition of functions, has a lot of very important applications. Well, let's look at some more specific examples to get a handle of what's really going on here. So again, we're talking about the chain rule, and my first example is to define f as a function of u, okay? And it's just defined as u squared plus 3, that's it. Just think of u as its input, that's all that matters. So u is f's input, and all I do with that input is square it and then add 3 to it. And u in turn is a function of x, all right? And u defined as its input x is just cube it, cube the input, x cubed, all right? And so if I can think of, if I want to find the derivative of f, okay, with respect to x, then what I need to do is, f is not a function of x explicitly. We can see that here. It's a function of u. So to figure out how f changes with respect to x, I have to first find out how f is changing with respect to its input, which happens to be u, and then find out how u is changing with respect to its input, which is x. Okay, so I have a chain of functions here. Really what's going on here is f is a composition of two functions. Okay? And so what I do is I have to find out first how f is changing with respect to its input, which is u. Multiply that by the derivative of u with respect to its input, which happens to be x. Okay? And again, if we cancel out the du's, we get back to df dx. So in order to compute this, I just have to find the derivative of f with respect to u. Okay? Just ignore u, what u is for the time being, and we just think of f as a function of u alone. Okay? And it's a normal derivative. We're just going to take care of the power rule here. Derivative of a constant is 0. Okay? So when I take the derivative with respect to u, I just get 2u, and the derivative of 3 is 0. And I multiply that by the derivative of u with respect to x. So I'm ignoring f now, and I'm only thinking of u in terms of x. And the derivative of this function with respect to x is just take the derivative. So we're doing the usual power rule here. And so what happens is this is just 3x squared. Okay, so this is how f is changing with respect to u, and this is how u is changing with respect to x, 3x squared. Now recall that I'm looking for the derivative as a function. In this case, I'm looking for the derivative as a function of x. So I want this all in terms of x's down here. And so to do that, all I do is replace u with its rule in terms of x, which is I cube the input, which is x cubed. Okay? So I rewrite this as, this is 2x cubed multiplied by 3x squared. Okay, so df dx is this quantity. And I could simplify this a bit. So f prime with respect to x is going to be 6x to the 5th power. Okay? And that is the derivative of f with respect to x. And notice again, because f is not a function explicitly of x, I have to do a chain of derivatives, because really this is a composition of two functions. And I can rewrite this, by the way, as this is the same thing as f of u of x. Right? It's a composition of f, in fact, of two functions. In particular, it's f composed with u, which is in turn a function of x. Okay? So this is f composed with u, or f of u. Okay? Fog, in this case it's fau of x. Okay? So f composed with u. And again, all I'm doing is computing the derivative. It's a chain of functions, therefore it is a chain of derivatives, and thus the chain rule. Let's look at another example. In this case, I'm again talking about the chain rule, and I've defined h as a function of x, but in this case it's not so clear as to what is the outside function and what is the inside function. I haven't explicitly told you what's going on here. So in many cases with the chain rule, the hardest part is to try to determine how this is an actual composition of functions, and when in fact you use the chain rule. Okay? So let's think of this, rewrite this in terms of a composition of functions. That's the first thing to do whenever dealing with a function that looks of this form, okay, when using the chain rule. So what I'm going to do is I'm going to rewrite this as, I'm going to think of f of an input, and I'm not going to write x, but I'm just going to write it as an input, as a dot. Okay, so whatever that input is, it's the same thing as the cubed root. You can kind of see that's what's going on here, right? It's something to the cubed root, and then there's something inside which is a function of x. Okay? But certainly I can rewrite the cubed root of x as that same input raised to the 1/3 power. Okay? And the inside piece here I can rewrite as g of x. This is x squared plus 2x. Okay? So I'm just going to rewrite h as a composition of two functions. And that way it'll be more clear what we're actually doing in terms of using a chain rule. Okay? That this really is a composition of functions. let's rewrite h. So in this case, h of x is definitely f of g of x. Okay? Where this is now equal to, again, f of g. If I put g in here for my input for f of g is just going to be g, the cubed root of g, and that's g to the 1/3 power. Okay? And so I just think of this as my g. This is my function in here, which is g, which is a function of x. And h is actually just f of g of x, right? It's just g, which is x squared plus 2x, the cubed root of that. Okay? So hopefully you can see that this is really a chain rule. Okay? And let me take the derivative of this thing. That is, remember that if I wanted the derivative of h with respect to the innermost variable, which is x, okay, I have to go through f first and then through g. Okay? So this is the derivative of f with respect to g multiplied by the derivative of g with respect to x. Okay? Again, I want to find out first how f is changing with respect to its input, which is g, and multiply that by how g is changing with respect to its input, which is x. Okay? So if I rewrite this, the derivative of f with respect to g, well, here's f as a function of g. Okay? So just think of g as only the input. That's it. Okay? And if I just think of this, and it's its input, which means it's the variable. Okay? So if I just think of f as a function of its variable, which the variable just happens to be g, I want to take the derivative of this guy. Well, I can just use the power rule on this. That's it. G is just a variable. Okay? So if I use the power rule, the 1/3 comes down. I'm left with my input, or my variable, and I subtract 1 from the 1/3 power. Okay? So it's 1/3 minus 1, which is a minus 2/3. So this is to the minus 2/3 power. Okay? And then I multiply that by the derivative of the g with respect to its input. G's input is x. I know how to take the derivative of this with respect to its input, and I know I can just use the power rule again. It's the power rule and the sum rule here. So this is multiplied by the derivative, which is going to be 2x plus 2. Okay? You see that? This is the derivative of g with respect to x. Here's g. And this is the derivative of f with respect to its input, which is just g. Okay? Now I'm going to rearrange this, and I want to put the negative exponents down below. So this is the same thing as 2x plus 2, hopefully you can recognize, over 3, and this is g, the cubed root of g. Well, this is g to the 2/3 power. I'll just write it that way. Okay? But again, I want this in terms of x. Right? So I'm going to rewrite g in terms of my x because it's a function of x. And so when all the smoke clears, what happens is my dh dx is just going to be equal to 2x plus 2 over 3 times g, which is x squared plus 2x raised to the 2/3 power. Okay? And that is, in fact, the chain rule. That's all I have to do. So again, the hardest part of this problem, and problems of this form, is to actually recognize that this is a composition of two functions. And then we can apply the chain rule.